Good morning, everyone. Congratulations to all the women present on International Women's Day. Welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 64 of this seminar. Today we have two excellent speakers, Jean Michel Coron and Iván Moyano. Introducing Jean Michel Coron, we have the Professor Diego Sons. Thank you, Diego. You can start.
Okay, so thank you very much, Juan, for the opportunity to introduce Professor Jean Michel. So Professor Jean Michel, it's a great honor to all of us have you here in this webinar. Professor Jean Michel Coron is a French mathematician. He's working on control, but also in have worked on elliptic PDEs, and they have great results in elliptic PDEs and also in control. And Professor Jean Michel Coron has received many prizes, like the Fermat Prize in '93, the gold medal of the French National Center for Scientific Research in 2016. And so, Professor, it's a great honor to receive you here. And today, Professor Jean Michel Coron we talk about controllability and stabilization of PDE control system with crucial quadratic terms. So, Professor, you have the word.
Thank you very much, Diego, for the very nice introduction. Very kind. I want also to thank Jean Limaco for the invitation, and also Enrique Fernandez-Carrà, who also was participating to this invitation. So, as it was mentioned, the talk will be about controllability and stabilization of partial differential equation, where there is a quadratic term, which is crucial for the goals that you want to achieve. So there are two goals. The first one is controllability, and the second one is stabilization, and we are going to explain more on this. And for the controllability, we are going to study KDV control system, a water-term control system. We are going to recall some results about small-time local controllability for some PDE, and then we are going to give the main ideas of our obstruction to small-time local controllability for the KDV equation. So the KDV equation that we are going to consider was introduced in 1997, the control system, by Lionel Rosier. So this is equation 1 that you can see on the slide, yt plus yx plus y triple x plus yyx is equal to 0. This is the usual de Vries equation, which is used, for example, to model the height of the water inside the channel. And there is some boundary condition. The length of the channel is L, and there is some boundary condition. First, there is a Dirichlet boundary condition. Yt0 is equal to Ytl is equal to 0. And there is also this boundary condition on the Neumann boundary condition, Yxtl is equal to U of t. And this is a control system where the state at time t is a function y, which is going to be in L2 of 0L. And there is also the control U of t, which is a scalar. And you are interested in the controllability of this equation, which is, for example, if you have y0, which is the initial state, and at time capital T, it is possible to move, thanks to the control, from y0 to y1. This is the problem of controllability. And the first idea is to study the case where y0 and y1 are small. And then, in order to study this problem, as it follows from the inverse mapping theorem, we study the linearized equations. That is, we forget the term yx. So we have this linear control system. Now yt plus y triple x equals 0, and the boundary conditions, which are the same because they were already linear. And that was studied by Lionel Rosier in 1997. He proves that this linearized control system is controllable in time t, if and only if the length is not critical, that is, if and only if the length does not belong to this set n, which is defined by equation 3. Not only that, he proves that in the case where the length is critical, that is, L belongs to n, then the uncontrollable part of the linear system is of finite dimension. It's a linear space of finite dimension. And then if you have this result, you want to study the notion of local controllability in time t, what it is. You have this 0, and you ask that whatever is the red ball, there is a smaller one, the blue ball, such that if you have 2 points in the blue ball, the two states, y0 and y1, it's possible to move from the first state to the second one, and you arrive at time capital T, you arrive at y1 by using a control which is small. Of course, we have to specify what are the norms for y0, for the state, for the control. So in finite dimension, it does not matter too much, but for PDE, of course, this is an important issue. But from the fact that the linearized system is controllable, you can expect that you can get a local result for the nonlinear system by using some inverse mapping theorem. And Lionel Rosier proves that this is indeed the case. In 1997, in the same paper, he proves that for any capital T which is positive, if the length is not critical, then the control system is locally controllable around 0. It's possible to move from y0 to y1 if y0 and y1 are small, and you can make it with a small control. But it remains open to understand what happens if the length is critical. If the length is critical, what is the situation for this problem of local controllability? If you look to the linearized system, it's not sufficient to get it because the linearized system does not satisfy this property. And the case where the length is critical was studied in these two theorems. The first one is the case where the dimension of the linearized system, the linear part which is not controllable, is of dimension 1. Then we prove that the control system, thanks to the non-linearity, thanks to the quadratic term, is in fact locally controllable, whatever is the time capital T. And there are many lengths which are such as the dimension of m is equal to 1. For example, L equal 2 pi, which corresponds to k equal L equal 1. It gives you some m which is of dimension 1, which is spanned in fact by 1 minus cosine of x. And there are infinitely many L such that m is of dimension 1. Now, if the dimension of m is larger than 1, that was proved by Serpa and Crépeau later on, that there is some time capital T. If you have the L which is critical, there is always some time capital T, such that you have the controllability in the time capital T, the local controllability in time capital T. And the proof relies on some power series expansion. The idea is very simple. You look first, you expand in power the control and the state. If you look to the order 1, you get the linearized system, it's not sufficient. Then you look to the order 2, to the order 3, and so on. And for example, if the dimension is equal to, of m is equal to 1, the order 2 doesn't give anything. You have to look to the order 3. And the fact that this is the order 3, which is odd, is used, in fact, in order to get a small time local controllability. Because if you can move in some direction in small time, you can move in the opposite just by changing the sign of the control. But if this is the order 2, this is not so clear. And so the problem is this. You assume that the dimension of m is larger than 1. Do you have the small time local controllability? And the answer is no. It's not always the case. So you have the length which is critical, so it's given by 5, and you assume that k and l, which are positive integers, are such that 2 times k plus l is not a multiple of 3. Then you get some obstruction to small time local controllability. You need to have some time in order to have the local controllability, even if the speed of propagation is infinite. And the obstruction, as I mentioned before, it depends on the red ball, the blue ball. There's some norm for that, and the blue and the red balls are with the norm H3 intersected with H1, 0. And for the norm of the control, it is H1 of 0, T0. Then you have some obstruction. You cannot go if there is some Y0 such that which is very small, but you cannot move to 0 exactly if the time is too small. But there are some open problems. So of course, in the talk, what is more important are the open problems. And here is the first open problem. we do not have the result in the physical space. The physical space are y is in L2 and the controls in L2. It's open in this space. We do not know if we have some obstruction to small time local controllability. And this is very important because there is some counterexample by Bournousou in 2022 for a Schrödinger equation. She gets that for some space, you do not have the small time local controllability, but for some other space, you have the small time local controllability. And it's very challenging to understand in our situation what is really the case where you consider the space in the state in L2 and the control in L2. And in the fact for the case of some other boundary condition, yt0, y equal yxtl is equal to 0, and yt0 is equal to u of t. So this is a new control system. There are some critical lengths. There are some good space where this is well posed. And OIMIN and BN in 2023, just a few weeks before, got the optimal result in this case. As was in the good space, and there is no, it's equivalent to the fact that the linear system is not controllable. Because in our situation, there is still an open problem. Our condition is that 2 times k plus l is not a multiple of 3, but it is stronger than the condition dimension of m is larger than 1. So the natural open problem is it sufficient to have the dimension of m larger than 1 in order to have that an obstruction to the small time local controllability? This is an open problem. And the last open problem that I want to present is the fact that what is the minimal time for local controllability? Because we know that we can control the system if the time is large enough. It's not possible if the time is too small. What is the optimal time? This is very challenging open problem. And for the water tank control system, I am going to present also some results without any proof in this case. Let me first introduce the system. So you have a tank, which is a 1D tank. You have some water inside the tank, and the control is a force that you apply to the tank. And we use, for the modelization, we use the Saint-Venant equation, which is an hyperbolic equation. So you have a problem now of finite speed of propagation. So you have, in any case, you have some obstruction to small time local controllability. But the point is, what about the time? And if you want to study the problem that we want to study, is just we want to move a little bit. We start with the tank is at some place, and you arrive to a tank is at some other place. At the beginning and at the end, the water is at rest, the speed is 0, and the height of the water is flat. And this is the same when you arrive at the new position. So the problem is, can we make it? Let's assume that D1 is very small. Is it possible to make it? The first attempt was done by Dubois, Petit, and Rochon, and they consider the linearized system. And for the linearized control system, they get the optimal results. You can make this motion if the time satisfies the condition 7. HE is the height of the water at the equilibrium. L is the length of the water tank, and G is the gravity constant. But for the non-linear case, then there is some new, we need more time. If the time is strictly less than 2 times the square root of L times HE divided by G, which is larger than the other one, it's twice the other one, it's not possible to do this motion for the non-linear system. So this is an example where the non-linearity is not helping you. There is a motion that you can do for the linear system. You cannot make it for the non-linear system. And it's possible to prove also that, in fact, if the time is large enough, then you have the local controllability of the non-linear system. So this is an example where now the non-linearity is a problem. So there was some prior obstruction to small time local controllability for partial differential equation. I would like to present some of them. And the first one was a problem suggested by Pierre Rouchon. This is a quantum particle. You have a quantum particle, so there is a wave function of the quantum particle in the box. So psi is in L2 of the row of the box, and it's the norm is 1. And the control is the motion of the box. And you want to know if the system is controllable. Let's assume that, for example, now you have the first eigenvalue of the Laplacian with the boundary condition, which is a Dirichlet boundary condition. You start with some psi which is close to this first eigenvalue. Is it possible to move, by moving the box, to this function phi1? And there is the analogous of the water tank problem. You start from phi1. You start with phi1. Is it possible to move the box a little bit and arrive again at phi1? You can also ask for some global result. Is it possible, for example, to move from the first eigenvalue to the second one? And there was some result. Let me just mention the first one. The first one, because this is the one in which we are interested in. If you do the linearization, then you can make this problem, sorry, the motion of the box, it's possible to make it for the linear system. And again, what I prove is that it's not possible to make it for the nonlinear system. And let me give you some idea of the proof. So you have the wave function. Let me give you the equation for the control system. D is the position of the box. D dot is the speed of the box, which is called S. And you have this control system. The Schrödinger equation, which is 9. The control is U of t. You have the boundary condition, which is a directly boundary condition. S dot is the acceleration of the box. S dot is equal to U. D dot is equal to S. And you have the initial data, which is psi1. S0 is equal to 0, and D0 is equal to 0. And you want to move a little bit, and you want to arrive at time capital T with S of t, which is again equal to 0. But T of capital T is maybe 1 millimeter, very small, but not 0. In order to get the obstruction, I'm not going to enter into full details, but you introduce this function theta, which is given here. And then you introduce this V of t, which is given on the slide. And if you compute V of t, you can see that V of t is given by 15, where V0 and V1 are given just below. And the key point is that for V0 is like S of t, okay? You can do, there's some extra term, but they are small. And so in some sense, you see, if you look to capital V of t, you start, so you get something like the integral from 0 to t, or S of tau, S of tau. So you have something which is positive, okay? And this gives the obstruction because we have some quantity which should not have any sign, which has a sign. And this is the obstruction to the small time local controllability of this control system, just if you want to move a little bit the box. And there was also some very interesting problem which was studied by Frédéric Marbach for the Burger's control system. So you have this Burger's equation. The control is U of t, does not depend on x. It's just a constant control, depends on time. Boundary condition, which is at the directly boundary condition. There is a very challenging open problem about this equation. Is it locally null controllable? If you start with some y0, which is small, can you arrive to 0 at the time capital T? And this is completely open. We do not know. What Frédéric Marbach got is that this system is again not small time locally controllable. There are some initial data which are small, so that you cannot go from this initial data to 0 in small time. And the proof of Marbach use also power cell expansion, new quadratic estimates, which are very clever. And there was also some change of time scales that I'm going to explain later on. And there are some other obstructions. One, the Schrödinger equation with bilinear control by Karim Bochard and Morgan Morancé, and the nonlinear parabolic equation by Karim Bochard and Frédéric Marbach. Of course, this obstruction again are not relying on the speed of propagation. It's not does not come from the fact that there is a finite speed of propagation that for the wave equation, for transport equation, all the equations that we are considering, except the water time control system, but the problem was different. The KdV equation, the Schrödinger equation, the speed of propagation is infinite. And the idea is always the same. You want to find the quantity which should be unsigned, but as a sign, whatever is the control. And this is the idea. But of course, the difficult part is to find this quantity and prove that it has a sign. In our situation, the novelty are first that we are going to consider boundary control. This is in contrast with the previous problem, where the control was inside. And boundary control are more complicated because, in some sense, you know that in finite dimension, in order to study the controllability of the system, you use iterated bracket. And we do not know how to make it, especially for the case of boundary control, how to make it for PDE. And this is very challenging or interesting problem to understand how to use iterated bracket for PDE with boundary control, for example. And also, for example, for Frédéric Marbach, he do a change of time scale, which introduce instead of the Laplacian, you have epsilon the Laplacian, where epsilon is small, but then you have a boundary layer which appear when epsilon goes to 0. For the Burger's control system, this is the heat equation. We can handle the boundary layer. But for the KdV equation, it's not known how to understand the boundary layer. And moreover, the last difficulty comes from the fact that you can write this equation as yt, it's a linear system. Yt is equal to ay, where a is linear. But in our case, a is not self-adjoint, not skew-adjoint, in contrast with the case of the Schrödinger equation or in the case of the Burger's equation. So what are the main ideas? Now I would like to present some main ideas, and we are going to start with the case of a finite dimensional control system. So we have this control system in finite dimension. The state is of dimension 3, y1, y2, y3, and the control is of dimension 1. y1 dot, d1 over y1 over dt is equal to the control. y2 dot is equal to y3. y3 dot is equal to minus y2 plus 2 times y1 u. And the state is y1, y2, y3, which is in R3, and the control is u in R. You want to study the local controllability of this system. The first thing that you want to try is to look for local results. So you linearize the system around 0, and the quadratic term, which is 2 times y1 u, just disappear. And you get the equation 20. y1 dot is equal to u. This is very good. But the other part is very bad because the control does not appear in this part and it's not influenced by y1. So the control has no effect on y2 and y3. y2 and y3 just turn around 0, whatever is the control. So the linear system is clearly not controllable. In this case, you can compute explicitly what are y2 and y3. And you get, for y2, for example, you start from 0 and you get y2 of capital T, which is given by this integral cosine capital T minus T, y1 square T dt. The control does not show up explicitly, but of course, y1 depends on u because y1 dot is equal to u. And you have a similar expression, a little more complicated, for y3 of time capital T. And if you look to 21, you see that if the time T capital T is less than pi divided by 2, the cosine is going to be positive. And then y2 of capital T is at least is larger or is larger than 0. It's more or less, it's more or equal to 0. So you have some obstruction. You cannot go to with y of capital T is equal to minus 10 to the power minus 9. So something very, very small but negative, you cannot make it. And if you look to 22, it gives you a better obstruction because let's assume that the time capital T now is less than pi. So this is a stronger assumption than pi, less than pi divided by 2. And if you want to have y1 of capital T is equal to 0, then you get that y3 of capital T is less or equal than 0. So again, you have an obstruction to the controllability if the time is less than pi. And this is the only obstruction. In fact, you can prove that if the time is larger than pi, you have the global controllability. It's even a global result in this case. Of course, it relies heavily on the fact that you have some expression of the solution. So this is 23 and 24. It's exactly what I mentioned. And not only that, if you have some perturbation, you see, you have some perturbation, but for some weight. So weight R1 is 1, and R2 this is 2, and R3 is 2. Because you see, if you go back to the equation, y1 is a size 1, u then has a size 1, y2 and y3 are the same size, but if you look to the third equation, you get that y2 has a size as y1 u, so it's a square compared to y1 and u. So the weight is given here. So the weight is here, 1, 2, 2. So if you have a perturbation for this weight, you get again an obstruction to the small time local controllability. Now it's not global, but small time. if you use some inequalities like 25 and 26. And this is what we are going to do. This is why I wanted to present it for this toy model. You have this obstruction, which is going to come from these two inequality. And you see that the inequality 26 is better than the inequality 25 because it gives the obstruction for the time less than pi. While 25 gives the obstruction only for the time less than pi divided by 2. Of course, on this toy model, there are many necessary conditions for small time local controllability in finite dimension, which relies on iterated Lie bracket. For example, in the case that I presented here, you can use a condition which is due to Sussman, a necessary condition for small time local controllability, which is not satisfied for our system. And this condition is just computation of iterated Lie bracket. And there are more general obstructions which was found recently by Karim Bochar and Frédéric Malbat. But unfortunately, as mentioned before, we do not know how to use, and this is very challenging, to use iterated Lie bracket for PDE, especially for boundary controls. But roughly speaking, we are going to follow 26. We are going to try to get something like 26 for the KdV equation. So our approach is inspired by the proof for of the positive results if the controllability holds if the time is large enough. So as I mentioned before, you do some expansion. You compute U is, you say this is epsilon U1 plus epsilon square U2 and so on. You do the same for Y, and then the YYX give you some Y epsilon square Y1X plus some extra term. And finally, you arrive to this equation. The first equation is just the linearized control system. We know it's not controllable, but we know that the part which it cannot control is of finite dimension. And then we have the second system, where is the key point. And you see now for the second system, there is this term, this quadratic term, Y1, Y1X, which is influenced by U1. And the idea is then try to understand what is the idea if you want to let's assume that the dimension of M is equal to 1, okay? Then the point is you start from 0 and you want to move to something which is in M, but not 0. Then the idea is for Y1, you find a control which allows you to move from 0 to 0, but such that if you consider Y2 start from 0, then Y2 at time capital T is not in M. It turns out that it's not possible if the dimension of M is equal to 1. It's not possible to make it. If you have the U1, which allows you to move from 0 to 0 for Y1, then Y2 is going to move from 0 to 0. So you have to use a cubic term for that. But also, I have to mention that the proof of the positive results relies on a contradiction argument. We assume that thanks to the other three, it's not possible to move in M, and you arrive to a contradiction, but it's not very explicit. And in for the obstruction, we are the obstruction to small time local controllability, the method is much more explicit. Of course, the computation are more complicated. And then what are the two steps? The first step, you classify all the control U1, which allows you for the linear system to go from 0 to 0. And then you see what happened to Y2 if you plug this control U1. That is, if you consider the equation 31, where Y1 is defined by U1. So this is the point. So first step, try to find all the control which allows you to move from 0 to 0. So for that, I just don't want to go in the details, but just to show you that it's complicated but explicit. So you first consider this equation, the cubic equation with some complex number. You have three roots. You define Q. The roots are lambda 1, lambda 2, and lambda 3. You define Q, you define P, you define psi, you define G, and you define H. So, okay, this is only definitions, yes? And at the end, you get holomorphic functions. G and H are holomorphic functions. And then the property is that the control is used for the linear system to go from 0 to 0. you get all the u. The u, if you take the Fourier transform, it has to satisfy 37 and also 38, which is related to Palais-Wiener. The first part, the u at absolute value of u at is less than c times c. The imaginary part of z is just the fact that the support of u is good. And the second part is the support of the solution y1 is good. Okay. Then you have this y1. Okay. You have this property, you have all the control which allows you to move from 0 to 0 for the linearized system. Then you try to understand what happened for y2. And for that, you have some new definition, you have this length. Okay, you have this number eta 1, eta 2, eta 3, p, and so on. You have this number, which are rather explicit but complicated. And there is this e, which is very important. This e, this is a complex number. And you have this property that, and this is where our assumption 2 times k plus l is not a multiple of 3 appears. E is not 0, which is going to be crucial for the proof, is equivalent to 2 times k plus l is not a multiple of 3. This is where we use the assumption that 2 times k plus l is not a multiple of 3. C is not 0 if only E is not 0. You have this now psi which satisfies the linearized control system, the linearized equation. And the key point is that psi satisfies 4 boundary conditions instead of 3. It satisfies 4 boundary conditions, and this is possible because the length is critical. The length is critical, allows you, and this is very exceptional, allows you to have 4 boundary conditions instead of 3, with a psi which is not 0. And then you do some computation, and you get this inequality, which is analogous to the inequalities I present before for the finite dimensional control system. We have this inequality 49. Y is the solution of the linearized control system. U is such that for the linearized control system, if you start from 0, you arrive again at 0 at time t, and you have this inequality. Now, from this inequality, you want to deduce something on y2. And so I recall you the equation. So this y1 is the same equation as y. This is a linearized system. y2, you see that the key point is that you have this term in the dynamics of y2. You have this minus y1, y1x. And then you have this property, which is exactly the property that we have here. 49 exactly is the same as here. And then the point is that this quantity is strongly related to y2, because you get that this quantity, that is the left-hand side of 45, is exactly 44. The left-hand side of 44 is exactly 45. And so you get this inequality. And for example, if you want to reach 0 at time t star, and if you start with something such that this is negative with a minus, then it's not possible to make it. And this is the obstruction to the controllability, the small time local controllability. And then, of course, then you have to take care of the fact that this is just a power series expansion. You have y1, y2, but there are some extra terms, but they are small. And so, roughly speaking, you still get the inequality 56, which is true for the full solution of the KDV system. So let me now move a little bit and then to make it very quickly. The stabilization problem. Now we look to something different. I'm just going to explain briefly the problem. So you have the same equation, okay? Yt plus yx plus y triple x plus yyx is equal to 0. The boundary conditions, this is the system that we saw before, and you assume that the length is not critical. If the length is critical, if the length is not critical, it's easy to check that you can construct a u, which is a function of y, even linear. Let's say that u is ky, such that 0 is locally asymptotically stable for the closed loop system, which is the equation y, boundary condition plus yx tl is equal to ky. In fact, you can get exponential stabilization with a decay rate, an exponential decay rate, which is as large as we want. And this was what I proved with Lucci, thanks to some transformation equivalence of system, where we introduced the problem of equivalence between two systems in the class of PDE, linear PDE equation. We start with the linear system, and then we move to the nonlinear system. And now we want to study to understand what is the situation when the length is critical. What can we do? Can we get feedback stabilization with the length which is critical, for the length which is critical? So we are, maybe I'm running, I think I cannot say too much, so I'm going to give the result. So I move to the slides here. Okay, so we have our control system, and the result is given on the next slide, and then I'm going to stop here because my time is over. So you want to find a u, which is a function of y, such that you have asymptotic stability. In fact, instead of asymptotic stability, we are going to get exponential stability. It's possible, and we have this result. Let me give you that. If lambda is positive is small enough, let me phrase it a little differently. If lambda positive is small enough, then it's possible to construct a feedback which depends on time, such that for the closed loop system, you have the inequality 2, where yc is the part which is controllable, and yu is the part which is not controllable. And you see that the weight, again, are different. You get that yc square, and here you have only yu. And you have an exponential decay rate, and then this is the initial data, t0 is the initial time, and you have this inequality, provided, of course, that this is a local result, that the norm of yt0 is small enough. And there are some open problems. I am going to stop here with these two open problems. The first one, our statement is that there exists lambda. If lambda is positive, small enough, then it's possible to have a feedback which gives you this inequality. And the problem is, it true that for any positive lambda, there is a feedback law which allows you to have this type of inequality. This is completely open and very interesting. And then there is also something which is very challenging. You see that the feedback that we construct depends on time. In finite dimensions, there are many examples where you cannot, which are controllable, but you cannot stabilize them by means of a feedback which depends only on y. You have to use a feedback which depends on t and y. But in the case of the KDV, it's not clear if it is really an obstruction. And so the open problem is it possible to get the same result, maybe for lambda small or maybe for all lambda, with a u, which a feedback law which does not depend on time, but it's a u of y. And this is an open problem. And I think I'm going to stop here. And thank you very much for your attention.
Thank you very much, Professor Jean Michel, for this very nice talk. So now we open the turn for questions or comments. So if anyone has some question or comment, please open your microphone and ask directly the question to Professor Jean Michel, or type your question in the chat as you prefer.
Discussion,
So,
okay,
Enrique, maybe.
I cannot switch on the camera. So
can you put Professor Enrique as a co-host?
I'm not allowed to, maybe.
Excuse me. I stopped sharing the screen.
No. Just a second, Professor.
Okay. Yes. Good evening.
Yes, glad to. I don't see you.
Thank you very much. Thank you very much for your talk.
No, it's okay, Enrique. You can share your camera.
That's okay? Okay.
Yes. Yes.
It's okay now? Okay.
Yeah.
Very good. Happy to see you, Enrique.
For your talk. From the argument you have presented on the obstruction, I think that not only zero, but you cannot do something that. Am I right?
Sorry, I didn't fully understand the question.
Yes, your connection is not good, Enrique.
Okay.
So can you repeat the question?
No, I said that the argument leading to obstruction does not permit to go to something that is small, not only zero, but you cannot get a final state that is sufficiently small. Is it right?
It gives you that, roughly speaking, it gives you that there is some half space, that you start from zero. Whatever you use for the control, assume it's small. If the time is too small, then you are going to move in this open space. You cannot go in the opposite. For example, typically, maybe I can go back to, maybe it's, roughly speaking, it's really the same as in finite dimension for this system. Maybe it's more clear with that. It's really like this. Let's look to y2. You start with 0. Y0 is equal to 0. And whatever is the control, if the time capital T is less than pi divided by 2, y2 will be greater or equal to 0. You cannot get y2 of capital T is equal to something, to minus something which is very small, but positive. It's not possible to make it. You start from zero, but it's not possible to do this motion. Okay.
Yes. No. Then my question, in fact, is if there is a sharp estimate or sharp description of the states that you can get.
Yes, this is very interesting. Not exactly. In this case, it's possible to make it in this for this simple system, but for the KdV equation, no, this is very interesting. It's very complicated because if the dimension of M is large, the part that which is not controllable, maybe you are going to get many obstruction of this form, depending on, we get an obstruction, but there are many others. So it's not really clear what you can achieve. Starting from 0, for example, this is very interesting open problem. What can you get? Starting from 0 with a control which is small and the time which is small, is it what you could get? It's not, it's very interesting, yes. I'm not able to answer to this question.
Okay, thank you. Thank you.
Is there any other question or comment?
Okay, so I stop sharing the screen and it's Ivan, now it's your turn.
Yes, so let us thanks again, Professor Jean Michel Coron, for this very nice talk. Thank you, Professor. You can stop to record one.
Thank you, Diego. Thank you a lot, Professor Jean Michel Coron, for your amazing talk.